Good morning. We're going to be talking this morning about Newton's law of gravity. Gravity. Gravitation, if you like. See how thick this book is. This is a 20th century account of gravitation. It's heavy. So some of the key features in this will be the law of inertia, the idea of a force, the idea of weight, the idea of mass, and gravitation. Mass and inertia are not understood. The whole thing begins with Galileo. Galileo lived in 1564, died in 1642. Galileo studied free fall. How objects fell. Galileo was capable of eliminating outside influences such as air resistance from his thinking. He came up with the law of inertia. The baseball there, in the absence of friction, would keep on rolling forever in a straight line. Galileo's law of inertia. Now, to study free fall, Galileo needed a timer. He came up with the first real timer. I mean, before this thing, timers consisted of egg timers or water timers, water falling through a small hole. How long did it take to empty a container? That kind of timer. But Galileo studied objects rolling down inclines. And for that he needed a timer. And for that, he noticed when he was in a cathedral that a lamp hanging, which is often you see in cathedrals, when the lamp swung, it didn't matter how big this angle was. Small angles of swinging had the same period. That's the time for a full swing. Over and back and over is a full swing. From here to here is half a period. The time for a swing we call t, the period, Galileo found to be constant. Nowadays we know it's given by 2 pi, the root of the length of the pendulum over the acceleration due to gravity. Here on the surface of the Earth it has a certain value. If you change the mass, that's not going to affect the period. If you change the angle, that's not going to affect the period. What will affect the period is the length of string. Nowadays we have a meter. A meter is designed to have a pendulum with a period of 2 seconds. That's what the meter came about. You design a pendulum with such a length that the period of oscillation is 2 seconds, or a half period, that is one swing, of 1 second. Sir Christopher Wren, I forget when he lived and died. Okay, so using his pendulum, Galileo studied objects in free fall, and he came to the conclusion that all masses, independent of their mass, fell at the same rate. I'll use the word objects. It's a casual word. Now, this rate at the surface of the Earth, Galileo found, and we now know, and we can find it today in a classroom, to be the acceleration due to gravity. Now, an acceleration works like this. After 1 second, if it's a constant acceleration, you're doing a certain speed. After 2 seconds, you double that speed. After 3 seconds, at constant speed, you triple that speed, and so on. Now, the acceleration due to gravity on the surface of the Earth is 32 feet per second per second. 32 feet per second per second. Seconds times seconds is second squared. 32 feet per second squared is in feet per second, but we like to use SI units. In meters per second, it's 9.8 approximately meters per second at the surface of the Earth. Up on Mount Everest, it will be less. Up on the moon, on the surface of the moon, the acceleration is approximately 1/6 of this. Yeah? On Jupiter, it's going to be a different value. Up in an airplane, it's going to be of a different value. It's going to be less, actually. So, there are many things that affect the acceleration due to gravity. We will see later on that it's the mass of the Earth and the radius and height. Radius of the Earth and the height above the radius. So, the acceleration due to gravity is crucial. Galileo's main achievement was to be able to ask the right questions. To see that studying mass, inertia, and gravity were relevant. And in fact, they are the most relevant things to begin natural philosophy with. The most relevant questions. Why do things keep on going forever in a straight line unless, as Newton says later, acted upon by an outside force? We don't know. It hasn't been figured out yet. One way or another, we have the law of inertia and the idea of free fall. Now, that's in the absence of air resistance, of course. You have to subtract air resistance in your head. Ideally, you could have a container and make a vacuum, carry out your experiments in it. And I think down in the Smithsonian Center, there's a vacuum whereby 2 feathers are dropped, or a feather and a marble or something are dropped, and they hit the bottom of the vacuum chamber together. So, Galileo. Now, Galileo died in 1642. Some people say 1643. 1642 is fine. The reason we'll stick with 1642 is because Newton was born in the same year. Isaac Newton. Isaac Newton formulated the 3 laws of motion. Galileo's law of inertia is the first one. The second one defines a force. If something is moving in a straight line, what does it take to change its course? And the answer is a force. If something is stopped relative to a person observing it, what does it take to get it to move? A push. A push will accelerate something. Accelerating it changes its state of motion. The acceleration is crucial. You try kicking a lump of lead this size, that'll hurt your foot. Mass has something got to do with it also. One way or another, inertia is back in play. Force is mass times acceleration. Double the mass, you need to double the force to get it to accelerate. It turns out later that force behaves mathematically as a vector. It has components in different directions. Alright, so force equals mass times acceleration. Newton's third law is not relevant here just yet. For every action there's an equal and opposite reaction. That turns out to be a statement of the conservation of momentum, recognized by Sir Christopher Wren, who was a great architect and designed London after the Great Fire, designed St. Paul's Cathedral. Sir Christopher Wren, he was a member of the Royal Society, as were all these guys. But Newton also formulated the law of gravity. just writing it down, but we'll come back to this little equation over and over again. The force of gravity is some number times the product of the masses divided by the square of the distance between them. That means nothing. I'm just writing it down to get it out of the way for you guys. We're going to spend all of the session here talking about it. Where did it come from? Where did the masses come from? What's the G? What's the R? What is FG here? Is it mass times acceleration again? That's a big question. Can I write it like this? Little mass, can it be cancelled? These are big questions. They're not fully understood. So, Newton's law of gravity. Let's see where it came from. First thing Newton realized was this. Nobody knows if he was actually ever sitting under a tree or not, but let's put him there anyway. Now sometimes the moon comes out in the day. If Newton is sitting up under his tree and the apple falls, what's the relationship between the falling apple and the moon? Well, the reason is the apple is in free fall. It's just heading towards the center of the earth. But so is the moon. It's also in free fall. Freely falling in orbit about the moon. Newton realized that the same force that pulls this guy also pulls this guy towards the center of the earth. He had to write down an equation to account for it. He had to invent calculus to work out the orbits of the planets. Using calculus, he worked out the orbits of the planets. All of his theory of gravity had some restrictions on it though. Newton's theory of gravity had to accord with Kepler's laws. So we look at Kepler. So the moon in free fall is pulled to the earth by the same force that pulls the apple. The same force that holds him sitting on the ground. Newton's cannon works like this. Think about the cannon. You can send a cannonball a fair distance and it will have a certain shape of trajectory. Parabolic. But you can use a bigger cannon, send it further. Eventually you can use such a powerful cannon that the cannonball can come back and hit at the back of the head. Famous BC cartoon. Let's see what were the restrictions on a law of gravity. If it's true, the law of gravity has to predict the motions of the planets. That's its job. It also has to be able to predict the value of the acceleration due to gravity on the surface of the Earth. It does that. Johannes Kepler, he was a mathematician. He was German, 1571 to 1630, right? He died, just I guess 12 years before Galileo died. They're contemporaries. Kepler lived a shorter life than Galileo. He had chronic illnesses, right? Anyway, Johannes Kepler, came up with 3 laws of planetary motion. Now, Kepler actually, I think, was a student of Tycho Brahe, who worked in Uraniborg and made observations of the planetary motions and the night sky without a telescope. And over the years, Kepler, formulated his 3 laws. The first one, I'll write things very briefly. Planets orbit the Sun in elliptical orbits. The second one. The orbital radii sweep out equal areas in equal times. What that means is this. When the planet is close to the sun, it has to speed up. When it's away from the sun, it can slow down. But close to the sun, the planet has to speed up. Gravity is pulling it stronger. Centrifugal force, if you admit its existence, balances the gravitational force. I'll talk about that later. I admit its existence. And away from, let's look at the orbit first. The third law says that the orbital period of a planet is some constant times the orbital radius, some constant squared times the orbital radius cubed. People say the period squared is proportional to the radius cubed. Now this number can be worked out by Newton's theory of gravity. Newton's theory of gravity accords with these three laws. Let's see what they say though. First of all, we need an ellipse. An ellipse is a figure with two foci. You can make an ellipse by getting a piece of string, nailing it here, and pulling a pencil around with it. You know, the ellipse has that shape. You can also make an ellipse by turning a plate on its side and watching its shadow. The orbits are only slightly elliptical, however. Kepler was devastated. He was devastated that God could make an imperfect orbit. Instead of making these circles, perfect circles, Kepler was expecting perfect circles, but no, they turn out to be ellipses. Now this ellipse is exaggerated. Comets, they could have exaggerated elliptical orbits, but our planets are only slightly elliptical. Now the sun is at one focus. These are the two foci of the ellipse. Now, let's look at the planet. And it moves from here to here in the orbit. The radius sweeps out a kind of a triangle. Let's say this is 1 day. From there to there, the planet moves some certain distance in a day. Now that's because it's close to the sun. When the planet is further away from the sun, it sweeps out another triangle, a narrower one, but the area of this one is equal to the area of this one. And that's the equal area law. What importance is that? That's a very important law. It's a statement of the conservation of angular momentum. If you study more physics, that will be very relevant. Ellipses, what's the relevance of that? Well, Newton's theory of gravity will come along and predict, using calculus, that the shapes of any orbits will be conic sections. Conic sections are the sections or slices that you can make from a cone. You can have a circle, you can have an ellipse, you can have a parabola or a hyperbola. They're kind of similar in shape. Doesn't matter, they're conic sections. The parabolas and hyperbolas are not closed. The ellipses, the general orbits, they are closed. The planet comes back to the same place every time with a certain period. T is a period. T is always a period for something repeated, some motion repeated, periodic motion, T. We will always have T in seconds. Let's look at the period of the Earth.